Hi friends. So today we are going to begin one more optimization tutorial, and today we are going to talk about what happens when you have maximum points and saddle points. Now there was a very interesting question on the channel, and this question was what happens when an optimization algorithm such as the ones we have been studying in this course encounters a point which is not a minimum point. So if you are dealing with a realistic problem every now and then, you will encounter points which are saddle points, which are maximum points, and so on. Now, of course, you know that in all these situations, the gradient vector is going to be 0 at that point. These are stationary points or critical point for the function. And so what would the optimization algorithm do here? We are going to look at this issue in today's tutorial. I am Dr. Ganguly. So we are going to specifically look at saddle point, maximum point, and minimum point. We are going to devise a very simple function for each of these cases and look at what happens with this function. We are going to make use of the Marquardt method, which we just studied in the previous tutorial, that is tutorial 21. Make sure you look at optimization lecture 21 for the Marquardt method. And again, remember, this method is xk plus 1 equals xk plus dk, where dk is the search direction which you can obtain if you know the gradient vector ck and the Hessian matrix H for the point xk. Now remember here, lambda is typically a large number and I is the identity matrix. Just to review the Marquardt method, we of course require the starting point x0. So this has to be given to us for a typical gradient based method. We select a lambda value. Typical lambda value could be lambda 0 is 1000. And then we proceed forward using this particular algorithm here. Now this is a linear system which you can solve provided you know h, you know lambda, and you know c. And once you have solved for dk, you can update your design using xk plus 1 is xk plus dk. Now there are two situations which happen in the Marquardt method. In case fxk plus 1 is less than fxk, then we set lambda k plus 1 is 1 by 10th lambda k. And in case fxk plus 1 is greater than fxk, then we say lambda k plus 1 is 10 times lambda k. So what actually is happening in the Marquardt method is that when you have high lambda, you are essentially using a kind of steepest descent method. And when you have low lambda, you are using a Newton method. So you can actually put lambda is 0 here and see that this will become the Newton method search direction. And if you put a very large value of lambda, for example 1 million, then you will find that it becomes the steepest descent method with the very small step size. So that's what happens in this particular method. We don't actually use a step size in this method, but you can think of the lambda as a kind of step size parameter here, or a learning rate. Let's now start with these three different type of functions we are going to look at today. So first I'm going to look at a saddle point type function, then a maximum point, and then the minimum point. Of course, the minimum point is expected to work well. We have seen that throughout this course, but let's start with a function which actually has a saddle point. So this function is fx is x1 square minus x2 square, and we are going to start from the point 1, 1. So if we take this function and we apply our usual knowledge of calculus to this function, then the gradient vector is going to be 2x1 and minus 2x2. So remember, the gradient is simply the partial derivative of f with respect to x1 and with respect to x2. Now the gradient vector can be set to 0. This is going to give us the critical points or the stationary points for this function. And we immediately see that the stationary point is x1 equal to x2 equal to 0. Now this of course tells us that the stationary point is given here, but whether this is a minimum point, a maximum point, or a saddle point can be figured out by looking at the Hessian matrix, which is the second derivative matrix. And for this function we can again differentiate these values here, and so we get h as 2, 0, 0, minus 2, which means that the eigenvalues of h are given by 2 and minus 2 here. Now of course you know that in this particular problem these are neither both positive nor both negative. One is positive, one is negative. So this is an indefinite matrix. So essentially whenever you encounter an indefinite Hessian matrix, you have a saddle point. Let's plot this function, and you can see I've done that in Wolfram and I have put it here, and this is the plot. So you can clearly see this plot looks like a saddle. Now for those of you who don't know, when you ride a horse, you typically have a device like this which is placed on the horse and the rider essentially sits here. So this is a saddle, and of course this is neither a minimum nor a maximum, but it has a situation where the gradient is 0 corresponding to the saddle point at 0, 0 here. Now we are going to unleash the Marquardt method on this function, but to do that let's first look at the function, let us look at the gradient, let's look at the H matrix, and we essentially define Python functions for these three values. So this is the first function which returns to us x1 square minus x2 square. Then we get the gradient vector here, that is 2x1 and minus 2x2, and we get the H matrix here which is 2 0 0 minus 2. Now of course remember Python starts with 0, so x1 becomes x0 and x2 becomes x1. Now we check for positive definiteness each time we calculate decay, and we do that because in general what is going to happen in the Marquardt method is that when you add h plus lambda I, you are going to get a positive definite matrix because lambda is a large value. So typically if we think of this h plus lambda I as h mod, then we can check for h mod whether it is positive definite or not. But of course when lambda becomes small, lambda becomes nearly 0, it can happen that you can encounter a matrix which is not positive definite, and in that case I simply replace h mod by I. That's a kind of safeguard into the method here or built into the algorithm here. Now one of the reason the H mod matrix should be positive definite is that that's going to satisfy the descent condition, and also positive definiteness makes sure that we have a non-singular matrix. Let's write the main program. The main program uses the starting value 1 1, lambda 0 is 1000. I essentially use numpy, and then I have a tolerance value which is a small number to check if the gradient has converged. I have a max value of 10. I'm going to just run this for 10 points because in many cases this algorithm is going to diverge, and of course lambda is 1000 here, and I print Marquardt method result. The Marquardt function is the key function here. It's going to take x0, tol, max, and lamb, and then print out the results for this problem. So this is the Marquardt function, and typically you see in this function that the first thing I do is I set x is x0, and then I create a I matrix here of dimension 2. I then have a for loop in range max. I calculate the gradient vector, then I calculate h mod as h plus lambda I here, and then I consider two possible cases in case h mod is positive definite, in case it is not positive definite. In case it is positive definite, I solve this linear system here using this built-in solver which is present in NumPy, and in case h mod is not positive definite, I replace it by I and I solve this system here. So this is essentially the pure steepest descent method. And then what I do is that depending on the particular fact, if x plus t is less than f of x, I divide lambda by 10 or I multiply lambda by 10. Then I print out the values of I, x, the design vector, lambda, and also whether the h mod is positive definite or not, and then I update the design x is x plus d. So this is the update here. I'm going to converge, or rather I will declare convergence when the norm of the gradient vector becomes less than tolerance. Remember, tolerance is the small number I sent in here, and so then I print converged x is x and break out of this for loop. Let us run this program. So I run it for this point here or this function here and this point, so you can see that here. So what's happening is that you are essentially diverging out of this particular problem. So again, this is of course interesting, to be expected. This method was devised for function minimization. You are looking at a descent direction and so on. So this is not working out, though it starts off that h mod is positive definite because of course I'm using a large value of lambda here. It does happen that toward the later half it is no longer positive definite and also it is slowly blowing up. Now, what would happen if I actually gave 0, 0 as the starting point? Remember 0, 0 is a critical point of this function. So C is 0, 0 here. So I do that here. I put the starting point as 0, 0 and I run this code with lambda is 1000. Interestingly, it at least declares that it has converged immediately because since I'm starting from 0, 0, the gradient vector is also going to be 0, 0. And so what this system is going to do is that it's going to have a 0 here, and so dk is also going to be 0. So essentially it is going to converge in the first shot here. So this is very interesting thing which you see here is that our h mod is essentially positive definite and we have converged at this particular point. Now here what I do is that I take a very small value here instead of 0, 0 just to see what happens. So I'm taking 0.001, 0.001 and I run this program here and then let's see what happens. Interestingly, with this value also you get the divergence. So this is something which is very interesting that we are getting divergence here even though we have slightly deviated from the 0, 0 critical point. What's happening is that the algorithm simply is not capable of reducing this function here to a minimum value and therefore it slowly starts blowing up. Now let's look at the second question, which is what would happen if we have a function which has a maximum point? How would a numerical optimization method typically work with this kind of function? And we use this function here, f of x is minus x1 square minus x2 square. You can clearly see that when both these numbers are 0, that's the maximum point. At all other points, this is going to be actually a negative number, so it's going to be below 0. Let's start with this point 1, 1. So before we do that, let's look at it mathematically. You can see the function here. You can set the gradient vector to 0. You know the stationary point is 0, 0. And the Hessian matrix comes out as follows, minus 2, 0, minus 2. And therefore, lambda is minus 2, minus 2. These are the eigenvalues of the H matrix. So therefore, H is a negative definite Hessian matrix here. This corresponds to a maximum point. If we plot this function in Wolfram, I get a situation like this here. You can clearly see there is a maximum point at 0, 0 here and all the other points are going to be below that. Now let us code all this stuff in. So we code in the function here. I have coded in the gradient vector and I have coded in the H matrix. So here of course you have to put in minus x1 square minus x2 square like here. Here it's minus 2x1 minus 2x2 like here. And this is minus 2, 0, 0 minus 2 like here. We now run this code and when you run it, you again do not get convergence, you in fact get divergence. So from 0.11 with lambda is 1000, the code is not able to converge. Again, the algorithm is made for minimum point, so if it encounters a maximum point, it is going to simply diverge. Let's put the value 0, 0 here, which is corresponding to the critical point of this function. And even from this point, you may expect something peculiar, but actually you get convergence because you are at this point. At this point, the gradient vector is 0, and we are actually checking only the gradient vector here to figure out for convergence. So actually the algorithm declares that it has converged. All it has converged is to a critical point here. It's not the minimum point. It's actually just a stationary point. Now do remember that at this point, since the gradient vector is 0, the new search direction is simply going to be 0. So as far as x is concerned, when we say x is x plus d, it's still going to be x. What about if we start from a slightly different point from the critical point? So if I start from 0.001, 0.001, I again start to diverge after a certain point of time. So this is very interesting. Just at the stationary point itself, you are able to converge, but if you are slightly off from the stationary point also, you encounter divergence because the point there is going to go in a different direction. The descent algorithm is not going to be able to do anything about the function here. Now let's come to the third case, which is the familiar case where this algorithm of course works. Now in all the papers, books and so on out there, you will encounter functions like this. So if I take a function like x1 square plus x2 square, you of course know the minimum point is going to be 0 and the x1 and x2 are both going to be 0 here. So let's subject this to the Marquardt method here with x0 is 1 1. So first let us treat this function to some math. So this is the function here. The gradient vector I can set to 0. I get stationary point is again x star is 0 0. Now the Hessian matrix is positive definite, so I know this is a minimum point. So this of course is a minimum point which is very nice, which is very easy to obtain. Let us see how it looks like next. So if I plot this function, it looks something like that. So this is typically what is known as a bowl-shaped curve. So you can clearly see the minimum point here in Wolfram. Wolfram is a very great tool if you want to plot any function. In fact, when I was a student, I didn't have access to tools like this. But nowadays you have tools like this which help you look at a function, and before you actually do any kind of design or optimization, you can sometime look at a function and see what it's going to perform like. So again, let's calculate the function, let's calculate the gradient, let's calculate the H matrix. So all these are coded in here as they are given. And so this is of course a very nice optimization problem. Those of you who know convexity, you know this is also a convex problem because the Hessian matrix is positive definite. It's in fact a strictly convex problem. So we would expect Marquardt method to do very well here. So let's start with 1 1. Let's start with lambda 0 is 1000. So we do that and let's see how it goes. So it goes very well, of course, as you would expect. You converge pretty rapidly and you converge to almost 0 here. Now this particular method, the H mod remains positive definite throughout, as you would expect, and as H mod decreases, it decreases to a very small value. So at this value essentially it is becoming a Newton method, and somewhere here it is a steepest descent type of method. The exact solution we know to be 0 0, which has been obtained here. Now, what would happen if I chose a small number? So again, it is like I'm perturbing the starting guess from the critical point or the stationary point, which I did with the maximum and the saddle point problem. So just for comparison, we should also do this for the minimum point problem here. So I've done that, starting with x0 is 0.001 and 0.001, lambda 0 is 1000, and I run this code here, and you can see that though I am pretty close to the minimum point, it takes a little bit of time, but then it does converge very quickly here. Now what would of course happen is that steepest descent is going to be somewhat slow, and remember the Marquardt method is going to start off with the steepest descent type of direction, so it is slow at the initial stages, but then it converges as it slowly moves to the Newton search direction as lambda keeps decreasing. So of course we know here x star is 0 0. Now I want to leave you with something very interesting which is part of the Newton method actually. So let us put lambda 0 is 0. So when we put lambda 0 is 0 here, then the Marquardt method essentially degenerates into the Newton method, and we start with the point 1 1, and in this case you see that Marquardt method immediately converges. And this happens because there is a particular theorem out there that if you have a quadratic function, it is going to converge in just one shot when you use the Newton method. And of course you can imagine why this is so. In the Newton method we are considering the function to be a second degree Taylor series approximation. So essentially we are keeping the gradient term there, which is the linear term, and we are also keeping the term involving the H matrix, which is the quadratic term. So any quadratic function, if you express it in this form and you are sufficiently near the root, then you are certainly going to converge very quickly. So that's what has happened here. So let me leave you with a more complicated problem for a homework assignment. So one of the things which most textbooks do, and we also have been doing in this course, is that we always specify some kind of starting design, and that makes life very easy when you often use gradient based method. But in real life, if you are doing a real world problem, you may not have a starting design, or a starting value of the x vector like x0. And also you do not know about your problem itself. Now many a time your problem may come from a computer code, and so you do not know whether your functional representation has a minimum point, a saddle point, or a maximum point. And so very often people encounter situations when they are dealing with problems out there where their code diverges. And maybe this could be happening because you have a saddle point, you have a maximum point. So you need to go and look at your problem more carefully. So anyway, returning to this function, this is the function here, e into x into y divided by e square, e to the power x square plus y square. Now what you need to do is find the minimum point, maximum point, and saddle point, if any, for this function. Now you could do it by plotting, you could do it by using the optimality criteria of setting the gradient vector to 0 and so on. And then what I would like you to do is to use any gradient based method of your choice. So you can use Newton, you can use conjugate gradient, you can use steepest descent and so on, and then try to find the minimum point for this particular function. And of course you are going to need some good starting design. So this problem is going to help you to figure out why starting designs are often very important when you are doing any kind of optimization problem. So let us culminate our tutorial today. So today we use the Marquardt method to demonstrate how optimization methods work when you have saddle points. Now, like I mentioned, saddle points often take place in many engineering design problems, many applied optimization problems, and very often people encounter saddle points. These may not be very useful from a design perspective. So you may need to do some parametric studies of the system to actually find out whether you have a saddle point or not. Now maximum points are also a problem, and if you are encountering maximum point, maybe you have formulated the problem wrongly. Remember that any maximization problem can be converted to a minimization problem by multiplying the function by -1, or you could take the reciprocal of the function. So look at some of those strategies. Basically, in the way we are looking at optimization in this course, we are formulating every problem as a minimization problem. Now in some fields they may actually try to solve maximization problems, but that's just a different way of looking at a minimization problem. And of course, if you have formulated your problem as a minimum problem or a minimization problem, you are lucky, and you can use the plethora of methods we have discussed in this course to solve that problem. So again, to recapitulate, this is the Marquardt method. Xk plus 1 is xk plus dk, where dk search direction is obtained by solving this linear system in pink. And fortunately, Python has given us a lot of tools in NumPy, which lets us solve this system in a very simple manner, which can also be done in MATLAB, for example. But of course, you can also use Python to do those type of problems. Now make it a point to look at optimization lecture 21 on the Marquardt method and on tutorial 21 on the Marquardt tutorial. And now that we know the Hessian matrix can be slightly changed and it still works out quite well, we are going to look at ways to actually create the H matrix, build it up using quasi-Newton method. So of course you all know that calculation of the H matrix is very difficult and cumbersome. In fact, the function I gave you today for the homework problem, you will find that calculating the H matrix for that function and coding it in is a very laborious task. So that is why the methods which rely only on the gradient vector are often very popular.